So I started this off giving you this very superficial overview of the heliophysics system. Just the two questions of why there is a magnetic field in the Earth and in the Sun and in some of the planets. And the answer was, one word, dynamo. They have dynamos. And then we said, but why does the Sun have a corona and why does it have a solar wind? And that said, because it has a magnetic field. And we showed how this magnetic field heated up the corona and led to this 1 million, 2 million, 3 million degree corona and then pushed this wind off into space. And then we took a break and actually heard from people who really knew what they were talking about before you had to hear from me again. And now I'm going to finish this by asking why it is that the Earth and planets, other planets as well, have ionospheres and why they have magnetospheres. And I'm going to start with the ionosphere part because there's our first part. Well, sorry, it goes backwards. Why they have ionospheres is because the Sun has a corona. It's emitting X-rays and EUV radiation. This is a simplified version of it. And so therefore it has an ionosphere. And now we know why it has a corona because it has a magnetic field. And we know why it has a magnetic field because it has a dynamo. Okay, so it sort of all works together. We took a bit of a break so we could really investigate the solar wind and the corona and some of the dynamos. And here is a cartoony version of the Earth's atmosphere starting from the ground here, which is 5,000 feet below our 5,000 feet below our feet, right? Going up in kilometers, 250 kilometers. Here's the temperature in Kelvin. You can see it drops off as you go up. And then we have the tropopause. And then the stratosphere, the temperature actually rises again a little bit. I mean, all of this is sort of to astronomical precision, somewhere around 200 and 300 Kelvin. And then it falls off in the mesosphere and then rises again in the thermosphere. Now, this is puzzling. It has a peak in the temperature at the stratopause, about 50 kilometers, which means heat must be added there, right? Because obviously the thermal conduction is going to take heat up and down. Down here, it's obvious why it falls off. The ground is being heated. The Sun is heating up our ground. So obviously heat is going upwards away from the source. But here it's going both up and down away from that source. And here it's mostly going down away from a source that must be above the mesopause. Okay, so what's all that about? And I'll give you a version of the answer, which I stole from this very nice picture in volume 3. This very nice figure. There's actually 3 figures I put in here. The first one I just introduced. We see the temperature falling, rising, falling, rising. And down here is a figure we've already seen, although I rescaled it so that it has a linear axis. This is the wavelength of light, 0 nanometers up to 400 nanometers. 400 nanometers, 4,000 angstroms. What's that? It's visible, sort of a bluey kind of color, right? And then everything here is ultraviolet, extreme ultraviolet, X-rays. Here in the red is the black body spectrum from the surface of the Sun, 5770 Kelvin. It falls right off. We've seen before that the radiation from the Sun sort of follows that down here in the visible, kind of falls a little below here, and then way above, right? If you were 5770, you would emit no X-rays, 0 X-rays. It's just falling like a rock. The corona emits X-rays because it's much hotter than that. So all this emission here is coming from the transition region in the corona. So we understand this plot. We understand this plot. This is the interesting one. This shows in color and I blocked off the color bar, but basically you can see the yellow, red, that's high amounts of energy deposition. This is the energy being deposited as a function of wavelength, as a function of height. So we have all this different, there's places where the energy is being deposited, and what we'll see is we have a big absorption, somewhere just shortwards of 300 nanometers, right at about 50 kilometers. Yeah, question? No, this is, yeah, this is a model, is it not? Jan, this is probably a model. This is a model. Yeah, right. So this is a model version of this. And we'll go through the details of why this looks the way it does. But there's the absorption of energy at that wavelength. That's what's creating the stratopause, right? That's what's leading to this peak because it's getting absorbed all in this wavelength here, ultraviolet. Right? This is what's doing all the absorption of the ultraviolet light. Now you go to very short wavelengths like the X-rays and the extreme ultraviolet. They're being absorbed much higher up. And this absorption, so I was telling Jan, this is the reason me as a solar physicist, I care about this. Because if you want to see the transition region of the corona, my favorite wavelength is 171 angstroms, 17 nanometers, and it's all absorbed up here at 200, 300, 400 kilometers. Right? So if I'm standing down here, even if I get up to 5,000 feet in Boulder, how much of the corona am I going to see? 0. So I got to go to space, get above all of this. But we've already talked about that, so let's talk about why this is happening, why all this absorption is going on in the X-rays and EUV region and also some in the ultraviolet region. And for this, I'm going to start doing a little simple mathematics. If I am a photon, Dana's favorite 171 angstrom photon, it's going to show him beautiful images of the corona traveling through the atmosphere. And I'm not observing at noon, so the photons are coming along a path that's inclined to the vertical by some axis chi. Okay? And I want to know what is the probability of my favorite photon there making it to some distance along the path. And we're going to basically parameterize the path by length L. Okay, or this maybe could have been a function of L or a function of Z, but it's just the probability that my photon gets to me. Now, if you remember anything about these probabilities, one of the things is you have to figure out what is the integrated cross-section of absorption of that photon. So I have a cross-section here, sigma, which is the cross-section for absorption of my photon. We'll talk about what the value of that is, but whatever it is, that's how I'm going to figure out my probability of surviving. Because I multiply that cross-section by the density of things that could absorb me, and I integrate it along a section of my path from wherever I start at the sun all the way to the position I'm considering. So this is actually telling me the total number of absorbers along my path. Now, if there's one absorber on my path, does that mean my probability of making it any further is 0? I've been absorbed? No. Why not? It's probabilistic, right? That means I have a high probability, I have a certain probability of being absorbed. So the probability is actually e to the minus the number of absorbers, or number of times I might have been absorbed, right? So if I have only one, my probability of actually being surviving, this is surviving, being absorbed 0 times, is e to the minus 1, okay? If there's 10 things along my path that could absorb me, then my probability of being absorbed is e to the minus 10. It goes down exponentially. So this integral, which is dimensionless, is called the optical path. Okay, and is the integral of the cross-section. So have people seen this kind of stuff? Just collisions, basically, how collisions work and how probabilities work? Good. All right, so now I'm set up to say, well, so what's that going to look like? Here, I'm going to actually try to do that integral, and I'm going to use the fact that the probability, I'm going to make a very simplistic assumption about the atmosphere. The density of absorbers, the density of things in the atmosphere, of molecules, is falling off exponentially with height. And capital H is the scale height with which it falls off. Anyone have a gut feel for what the scale height of our atmosphere is? I'm an astronomer, so you don't have to be very precise. What? Okay, good enough. I would say 10. But to an astronomer, 14 and 10 are the same number. So something on that order. That's how thick the Earth's atmosphere is. You know, people will ask you that, and it's like 10 kilometers thick. So it falls off exponentially with that scale height, and it has some value down at sea level. So I'm going to use that in my integral. Right? I'm going to take this n. I'm also going to just basically move sigma out, say it's the same photon, it must be the same cross-section. I'll move that out. And then I have this geometric secant of chi, which is telling me about, well, if you go in at an angle, you're going to go through much longer path to get to a certain height. Okay. But the important thing is this integral of e to the minus z over h, right? The number, integrating this exponential. And so now I get a optical path that is exponential. And what I'm going to do is I have this thing in front that's basically sigma n naught h and a secant of chi. I'm going to take the logarithm of that, basically turn it into z minus z tau 1. I've forgotten what they use in the textbook for this, but that just reminds me, this is the place that this integral would be equal to 1. Right? The place where my probability of being absorbed is my probability of survival is e to the minus 1. Okay? So I plug that in, and this is my favorite part, because what it means, so certainly here's the definition of z tau 1. It's the scale height, our 10, 14, according to Gilly, kilometers times this logarithm of this number. That tells me the height of tau equals 1. My probability of survival is, this is so cool. I love functions. An exponential of an exponential. You don't see that often, because the inner exponential is due to the exponential fall off of the absorbers, and the outer exponential is because that's the way probabilities work. They fall off as 1 over e, or as exponentials. So there's my probability of survival, and we'll work out a couple of things here. But say I have a cross-section that's something like, well, sorry, this is just another way of rewriting that. Let's not focus on that. Say I have a cross-section of, start down here, 10 to the minus 23 centimeters squared. It's a very small cross-section, but remember what you learned very early on. Molecules are small, okay? Photons are small. So the collision cross-section of a molecule with a photon is a small cross-section. If that were the cross-section, then basically z tau 1 would be about 50 kilometers. This blue line is this exponential of an exponential. You'll see it's 1 pretty much almost entirely above that, and then it just chops off to 0. Right? Exponentials fall off fast. Exponentials of exponentials fall off. The technical term among mathematicians is wicked fast. Sorry, from mathematicians from Worcester, Mass. It's wicked fast. This falls off very fast. So your photons just don't survive below 50 kilometers. A larger cross-section, they don't survive below 100 kilometers. Still larger cross-section. And you'll notice my cross-section is going up by a factor of 1,000, and I'm basically getting myself 50 kilometers. That's because that z tau 1 is logarithmic in the cross-section. Okay? So as I go up, I'm going to as the cross-section gets bigger, I'm going to survive. My probability of surviving to the ground is smaller and smaller. In fact, for none of these cross-sections will I make it to the ground. Okay, so this is basically how we figure out how photons are going to make it to the ground. Now let's see what those cross-sections are. And here is a plot, very simplified. This is the average cross-section. So there's lots of different molecules in the atmosphere that could be absorbing. This is sort of taking a weighted average of all the cross-sections of all the different molecules weighted by their abundance, the probability, the fraction that are that molecule. And you'll see, it's a logarithmic scale. It does go from sort of 10 to the minus 24, very small cross-sections, up to 10 to the minus 16. That's sort of, the area of a molecule, a little smaller than the area of a molecule. So if you were not a photon, but just a point, that's the sort of cross-section you'd see. Everything else here is actually seeing a smaller cross-section because photons and molecules are not natural allies, right? The photons will go past these molecules without ignoring them most of the time. Unless there's something particularly interesting about that molecule. If it has an energy, if it resonates at an energy like the photons, then it will have a particularly large cross-section. And down here, we see, this is the actual plot from the textbook, the different main contributors to that cross-section. Down here in the 2,000 to 3,000 angstrom region, what's happening is it's ozone, right? Oxygen 3, not our friendly oxygen 2 molecules, but this weird oxygen 3 that is doing most of the absorption, okay? So these molecules present a particularly juicy target for the photons when they're 2,500 angstroms, 250 nanometers, and therefore they get absorbed right there around the stratopause, right? And that is why we get that heating. That is why the ultraviolet is being absorbed. That is why we talk about the ozone layer, right? But for the shorter wavelengths that are the cool, interesting ones, they actually have a, anyone, this is angstroms, you could use nanometers. Anyone have an idea, if you're at 1,200 angstroms, what the energy of the photon is about? 121 nanometers. That one, because it's a particular. Yeah, it can be. Or it can be really cool. It's an awesome way to see the solar chromosphere. But that's, do you know about how many electron volts those photons have? Well, I'm an alpha. What's the, what? 13.6, that's actually 911. That's basically from infinity to n equals 1 in a hydrogen. That's the binding energy of hydrogen. So this is 3/4 of that. No, this is not 10.7. Oh man, that's way over there. Yeah, this is extreme ultraviolet. So that's sort of, let's just roughly say 10 electron volts-ish. Okay, so these are 10 electron volts. Our nice visible light that we see is like 2 electron volts. Okay, so these ozone molecules are resonating because they like sort of 4 electron volt photons, because ozone is a poorly constructed molecule. It rattles, right? This is like a bad car. It has a lot of rattle, and so 4 electron volts is enough to do it damage or knock some of its electrons into, right? So it has these loose pieces that are going to get absorbed at 4 electron volts. N2 and O2, those are solid, well-made molecules. 4 electron volts is nothing. They're not going to even notice it. But by the time you get up to 15 electron volts, you have enough to knock apart an oxygen atom. And this is basically telling you you can ionize O2 at that wavelength, 900 angstroms. You can ionize N2 at that wavelength. So all of this is absorption by basically ionizing these molecules. And that is why they have such a big cross-section. And these are wavelengths, these are energies of 15, 20 electron volts, even shorter here. Okay, lots of electron volts. Very short wavelength, very high energy photons. And so the cross-section has this structure, fairly complicated, because these are the molecules that the photons are interacting with, and this is how strongly they interact with them. And now we say, well, if I know that cross-section, z tau 1 is just the logarithm of that cross-section divided by something. And so the cross-section does that. So z tau 1 does exactly that. And so our probability of surviving does exactly that, right? So we get absorbed at 150 kilometers if we're at this short wavelength, because our cross-section for absorption is 10 to the minus 16, 10 to the minus 16 centimeters squared. Okay, so it's all encoded in there. So far, so good. That's what happens to the photons. Now, when those photons are absorbed, and they do their ionization thing, they're actually depositing their heat. So the actual energy flux is whatever it is at infinity times the probability that I'm going to make it with that energy. Okay? And the deposition is the derivative of that. Right? If that amount of energy is falling off, then the derivative of that is how much energy is lost between one place and another. So now I get to take the derivative of an exponential of an exponential. And it brings down another exponential. You do a little math. You get this even more interesting function, an exponential of an exponential minus a linear function. Okay? This is the heating that we were seeing. Here, now I've plotted this on a log scale, so the wicked fast drop-off looks even wickeder faster. And the red is that derivative. And what's even more interesting about this function is how that derivative sort of has a very hard bottom and then falls off in the top. This is the amount of energy that's being deposited as a function of height if my cross-section is that, if my cross-section is that, if my cross-section is that. This is where the energy is being deposited. And so basically that's what's giving these colors here, right? So the color here, you can see it falls from yellow through red, blue, black, really fast at the bottom and slower at the top. And this is I think this is a logarithmic color scale. So, right? So that even shows you why this has that shape it does. This is the energy being deposited, and if you're sort of up here, you're getting 300 milliwatts per square meter per nanometer out in the flat part of the spectrum, and it falls off, I infinity falls off. And so one of the reasons this is so bright is not because the absorption cross-section is so small, because it's very small here, but simply because there's more photons here. Right? The spectrum is much higher here than it is here. So you're absorbing all of the photons here, but there just aren't that many of them to absorb. Over here, there's a lot more to absorb. Okay? So that is the sort of structure of how this energy is going down into the atmosphere and then not quite making it. And so I really have to blame for the vast expense of my field of study that we need $100 million, billion-dollar spacecraft to do this kind of observing. I can't blame the ozone layer. Right? Ozone is not responsible. I have to blame oxygen and nitrogen, which have some other benefits to my life. So I'm sort of going to take the bad with the good. So it's those that are doing it. And actually, every time they're absorbing these photons, they're being ionized. So this is the real story of the ionosphere. Now we just talked about photons. These things are actually creating electrons. Here is, okay, so it's creating both electrons and ions, right? It basically knocks off. So here's a nice little chemistry diagram. I don't do chemistry, so I don't really fully understand this. But essentially, this is an oxygen molecule being ionized and creating an oxygen molecule with a positive charge. So it's giving up an electron. And there's the nitrogen molecule being ionized. There's an oxygen atom all by itself. If it sort of wasn't bound to a partner, it would get ionized and create O+. Here's all of these. This kind of stuff is only going on in this region here. This region here, that's photons coming from the transition region and the corona, because these are the only photons that have enough energy to ionize the atmosphere. Now I have plotted here, instead of the temperature, I have plotted the number density of electrons. Someone else plotted it, because I would have said per cubic centimeter. Someone else used per cubic meter. 10 to the 8 per cubic meter, 10 to the 12. If you're used to normal units, this is 10 to the 6 per cubic centimeter, right? So we have plasma densities that, for the solar corona, are very no, sorry, these are electron densities, are very small. But this is being maintained in the Earth's atmosphere. And you can see the plot as a function of height. We get quite a bit of free electrons bouncing around during the day and less at night, because we don't have the photons to create them at night. Actually, that's kind of puzzling. Why would I have any? I got no photoionizations. It's dark at night. Second thing I learned in graduate school, it's dark at night. I was working all the time, so how can we have any electrons at night? This is not, as I said, this is not a great number, 10 to the 3 per cubic centimeter, but it gets up to like 10 to the 5 per cubic centimeter in the middle of the night. Mika. What? It does, and I think Jan may tell us more about that. And I understand you are the manager of the eclipse, as I understand it. So you control it. And so if anyone gets upset that the sun has disappeared, I'm sending them to you. No, let's just talk about day-night, with which I have a lot more experience, and then we'll get to those things. Right, but why isn't it zero? All this stuff I talked about, absorption, ionization, it's not going on at night. Yeah. Okay, but I am looking at a place where it is night. And yes, you're right. So somewhere on the other side of the Earth, ionization is going on. Do you suppose those electrons and ions are making it?
Well, I'm asking what kind of transport goes on.
Yeah. Right now I'm thinking of no transport. It would be very hard to get stuff all the way around the Earth. Even FedEx would take a long time to deliver those electrons. Yeah. That might be contributing. I'm looking for something even simpler, though. We basically have a source of electrons, and it's turned on during the day. When I turn it off, that mean all the electrons go away? Well, it takes a while, right? They have to now recombine to form neutral atoms, and that is not instantaneous. That takes a certain amount of time. Okay? So actually, during the day, I said it was creating electrons. But if it was continually creating electrons, the number density would just go up and up and up and up and up forever until everything was ionized. It doesn't, because this is very similar to what we're talking about for creating the corona. When we have energy, you have energy in, you also have energy out. You have electrons in, you also have electrons out. And there's a balance between those two. So the real key is the recombination. Okay, I have this ion production, electron production that I've been talking about. There's also destruction of free electrons, which is basically them finding a positive ion and forming a neutral atom again. Now, the interesting thing is the production rate is proportional to the number of things that I can hit and create an electron, proportional to n. The destruction rate, I need to have two things to create a neutral atom. I need the electron that I created, and I need the ion. And the rate is going to go as the product of those two densities. And if basically for every electron I create an ion, that means the destruction goes as the density squared of electrons. This is the reason there's an interesting balance. The production goes as density, the destruction goes as density squared. So eventually, I can balance those two. Production can balance destruction. And the number density will go as, in equilibrium, will go as a square root. Okay, so I take the square root of my exponential of an exponential, and I get this, right, which is the number density I would expect during the day. And now we have to go into the fact that this is in equilibrium when the two balance. When I turn off the sun, be it by an eclipse or by an eclipse of the sun by the Earth, also an eclipse, a terrestrial eclipse, that happens once per day, right? Unless you're on in one of the polar regions, then it happens once per year. Yeah, so at that time, I have only losses, but I'm going to lose my ionosphere, I'm going to lose my free electrons at a certain rate, and the interesting thing is that rate is going to depend on the density squared. So here, we have a plot. I actually made this one myself, but basically took a lot of data off the web. Now, instead of energy, what color is encoding is the number density of electrons. Here we have the hours in a day, starting from midnight to midnight again, 24 hours, and it goes on to 25. I took this data from March 21st at 45-degree latitude so that I could sort of do all the math very easily in my head. What's magical about March 21st? The equinox. So I have 12 hours of daylight, 12 hours of night. I can figure that out. So the sun is up from 6 a.m. to 8 p.m. or 1800 if you want to say that. That's when the sun is up. Here is the density. Here's the altitude. I actually don't even show you anything below 100 kilometers because nothing's producing electrons below that. Then, this is, I apologize, I love making these really complicated plots. So along the top, I show the number density, now in normal units, as a function of time at 3 different slices. This bottom slice, next slice up is here, and then a slice way up here in dash dot. So the bottom slice is actually this. You can see when you're low down, the density goes way down. It doesn't go quite to 0, but it goes really far down. And then when the sun comes up, it goes way up there and then back down again. When I go through here, it gets even higher, but it doesn't go down quite as low because now the number density of electrons and ions is smaller, and so there's a time rate. It takes, this thing here has to shut off slowly after the sun goes down. And when I'm way up here, it shuts off so slowly, it basically doesn't get very far before the sun comes back up again. So we have sort of a recombination time up here that's longer than 12 hours. And so the modulation in this electron density is very mild up at the high levels and very gradual and very fast down here. I've also done vertical slices here so you can see these profiles. And this is this version of those profiles during the day and during the night. You can see that bottom portion just goes cruising right down, and up here it drops off by a much smaller amount. Okay. Does it increase again on the night side? Bottom's 100. Oh, down there. I'm going to say, since I made this plot, what does cause that? All right. Now I got to turn to Jan. Yes. Yeah. Oh. I'm not a nighttime astronomer. I don't know about these stars you're speaking of. Ah. All right. In the Earth's atmosphere. Okay. This down here. Yeah. Okay, thank you. Okay. Okay. From starlight itself. This is okay. There you go. I'm learning stuff here. All right. You see the very superficial level I understand this stuff at. Okay, so slightly more of the details here. I want to show you, so this is taken again from volume 3, and in all of the colors here, I have the density of all the different constituents broken out one by one. So in the dashed lines, we have molecules. Well, we have neutrally things, I should call them, because helium really isn't a molecule, but it's neutral helium. N2, O, O2, right? So this is, again, all above 100 kilometers. And their density's all falling off. I assume that the density of scatters falls off exponentially. The number density of electrons, and we see, aside from this interesting peak that we just had explained to us, we see here that in this region, the number density of electrons and the number density of O plus are very similar. So that's really the main source of these electrons. Ionization of the neutral oxygen atoms is what's really helping out here. But what I want to draw your attention to as a plasma physicist is if you compare the number of electrons and the number of O plus to the number of O neutrals, there's a 1,000-fold difference. This is actually, well, this is called the ionosphere, it's 99.9% neutral. Okay? The electrons and ions are really cool because they're actually the thing that's going to make this sort of a conductor, going to prevent radio waves from getting out because it sort of behaves like a metal. But that's the parts you see with radio waves, but that's only 0.1% of the stuff out there. It's mostly neutral. And as you go up, the fraction of the neutral fraction falls off. The electron fraction stays relatively constant. As you go further down, it's really bad. It's like 1 in a million. Okay. I want to just do a different puzzle that has nothing to do with the ionosphere. But I noticed these things all fall off at different rates. Why do they fall off at different? Why is helium sort of falling off very slowly with height, and oxygen, too, falling off like a rock? If I were up there, this is the stuff I need to breathe, so it's falling off very rapidly. Helium makes me sound like Donald Duck. That's not falling off so fast. Why do they have different heights, different exponential rates? I said there was one. Yeah. Molecular weight, right? They all fall off exponentially because they all have roughly the same temperature. However, they have the scale height h I was telling you about is basically the temperature divided by mg. M is the weight of the molecule. So if I change m, I change this scale height. And so we have 28 proton masses, a scale height of 43 kilometers. H, a height of, by the way, this is a bit hotter. Here we're in the thermosphere. So we're no longer 300 Kelvin. So this is sort of 3 times what we were talking about before, because this is sort of 3 times hotter than it is on the ground. But these other molecules fall off slower because of that. So oxygen is such a dominant molecule because it has a mass that's only 16. It has a scale height of 76 kilometers. Now that's only twice this, but it's in the exponential. So it falls off exponentially half as fast as oxygen 2. So by the time you get up here, now does this happen at the ground? As we go up into Boulder, are we all kind of dizzy because the fraction of oxygen has fallen off based on, from what it is at sea level? Based on this formula, you think it would. It turns out there's enough mixing going on from winds and things that it keeps the fraction about the same, right? This is actually also known as this is the troposphere, but it's sometimes known as the turbosphere. It mixes things up. It's once you get up here that those winds are not around that things kind of start to separate out. That's right. That's right. Just the lack of air pressure overall. But the fraction of oxygen is no different here. So let's sort of summarize here. Once we have, well, sort of give you an idea now of why this is interesting, it's only 0.1%, so how interesting could it be? The ions and electrons form this conducting fluid, this plasma. And a lot of us here have a lot of experience with plasma, so this is the part we're familiar with. And the neutrals are just forming a separate fluid, just a fluid of air. But these things are constantly trading places, right? We have this ionization going on. We have this recombination going on. So this couples the two fluids. In a sense, they kind of know about each other because they basically if you're an electron, you came from a neutral atom and you had some memory. This is very similar to the story that Marty Lee was talking about yesterday with pickup ions. Pickup ions are basically ions that used to be neutrals, and they have a memory of the fluid that they came from. Here, this is going to be each of the species has a memory of the other one because each of them came from the other one not too long ago. We have one ringer in the audience here. But say we get our density of electrons. It's a conductor, right? It may not be such a great conductor, but it's a conductor with a number density of electrons, Ne. That means it has a plasma frequency, which is this, Ne. I basically divided by the 2 pi. So this is not the angular frequency. This is the linear frequency in tens of kilohertz times Ne expressed in inverse cubic centimeters. This gets to be about 10 to the 6, right? When you have a conductor with a certain plasma frequency, if you put an electric field into that conductor, the conductor screens out the electric field. That's what conductors do. Their electrons all move, cancel out your electric field. If you're changing your electric field, the electrons may not be able to do that. That's where the plasma frequency comes in. The plasma frequency is basically how fast those electrons can do their job. Can screen out electric fields. That's their job. That's what electrons are supposed to do. So if you change your electric field faster than the plasma frequency, the electrons are stuck in their tracks. They can't screen out the electric field, and so you get to go through. So if you have an electromagnetic wave at frequencies higher than this, you will be able to propagate through this conducting medium. If it's lower, you're going to see it like it's a metal reflector. Right? Now, the number density of electrons in a piece of metal is much higher, which explains why metal is shiny. Right? The visible photons see this metal surface, and they think they can't get through. The plasma frequency is too high, even for 10 to the 15 hertz oscillations. The electron density in the corona, the ionosphere is much lower. So my question is radio emission. I want to observe the solar corona, right? That's all anyone would want to do. And I want to maybe observe it in the radio. That seems a little hard, but let's say I wanted to do that. What is the lowest frequency I could hope to see the sun in? We have one radio astronomer. You don't have to, please don't answer this question. You already know. I think we have only one radio astronomer here, but I know you are. Anyway, just based on the numbers we have so far, this formula or ham radio operators here? Jan, I bet you're a ham radio operator, right? Yeah, Jan, do you do ham radio? Oh, okay. Yeah, some of our engineers in our lab. It's a cool hobby, but it's a hobby of a bygone era. Oh, come on, guys, plug the stuff into the formula. What? Okay, I stand corrected. All right, anyway. I know. All right. So come on, though. Let's lowest frequencies. What frequency can I get radio waves through down to the ground from space? What? 10 to the 6 in the day. And actually, it doesn't fall that much at night, right? So here's a plot, right? At night, sort of gets down to 10 to the 5, but let's say 10 to the 6, oops, for simple math. 10 megahertz, yeah. So you want to do radio observations below 10 megahertz, so sort of the AM band is going to reflect, it's going to see the ionosphere like it's a big conductor. 100 megahertz, you're getting through. Okay. All right, so Now, another interesting part, we heard day-night changes. We also saw this plot before. The amount of X-rays coming off the sun, which is doing a lot of this ionization, varies quite a bit, a factor of 50 at this band pass anyway, between solar minimum, when there isn't that much of the closed field corona, which is the dense corona, which is emitting a lot of X-rays, and solar maximum when there's a lot of that. So this curve actually, I didn't draw your attention to it, there are two curves here, day and day, night and night. One of these is day during solar maximum, the other is day during solar minimum. Okay, that, very simplified. Right? We also have these little spikes, these flare events. Suddenly the X-ray flux goes even further up. This is, I think, a sort of specialty of Jan's. That increases the production rate even higher. So the ionosphere is going to respond to these flares because they ionize more of the atmosphere. Actually, here is a plot of, I believe this is from, I only gave your chapter. This is your plot though, Jan, right? Yes, okay. Volume 4, Volume 3, Chapter 14. Jan wrote it. This, we can blame him for this strange, this is the cycle here. This is the lowest flux. Is that right? Yeah, -1, whatever that means. Lowest flux of EUV X-ray photons up to the highest flux. And you can see the number density of electrons. The structure of the ionosphere is changing as well, but we have variation from solar minimum to solar maximum. Okay, so this isn't even solar minimum. This is like a super deep solar minimum that we haven't seen in 400 years. Okay. Oh yeah. This is solar. This is. Oh, the grand maximum. Okay. All right. Oh, I see. Yeah. So this is S's. Right. Okay. Yeah. So this in the theme of this school, this is telling us about the fact that with. Oops. Let me get to a couple more things before we take a little break. All right, because I want to get to, very briefly, other planets. We've been talking about the Earth, particularly fond of that place. But that has this atmosphere, a lot of nitrogen, some oxygen, very little CO2. Right? We're trying to work on that. And some water. Venus and Mars seem like very different places. A lot of CO2 in their atmosphere, some nitrogen, almost no measurable oxygen. So how does the story change? Well, you can see here, just plotted as temperature. It certainly, the temperatures aren't vastly different. Right? One of the lessons here. Venus, if you get down to the ground, it's vastly different. But in this region, Venus's temperature up in the atmosphere is not that different from that of the Earth or that of Mars. What really matters then is this diagram here becomes a little different, right? You have carbon dioxide creating the oxygen, but you have singly ionized oxygen as well. And so you get concentrations that look sort of different down here, but oxygen plus up there. And you're going to get basically ionospheres in those other planets. Okay, so I don't want to dwell too much on this. Just to give you an idea, this is not unique to the Earth. We have EUV radiation, X-ray radiation, ionizing the stuff in our atmosphere. That's what's creating the corona. That's what's creating the ionosphere. I want to keep saying corona. So we will take a break, but I'm going to leave you with a question. Say, hypothetically, I am a daytime astronomer, so this is very hypothetical. Say I were to discover an exoplanet, and of course I would name it Dana 1. It's a Jupiter, say it were a Jupiter-sized planet, and it's orbiting pretty close, 1 AU, And a star is a hot star. It's a B star. It's a main sequence star. B-type star means it has about 10 solar masses. Surface temperature, instead of this wimpy 6,000 Kelvin, it's 20,000 Kelvin. And it has 10,000 times the luminosity of the sun. Dana 1, cool planet. Is it likely that Dana 1 has an ionosphere? Think about this while you take your 5-minute break. And then say I were to discover Dana 2 orbiting in same parameters, except it's orbiting an M star, which is a very small star, 10th of solar mass. So I want to know Dana 1 or Dana 2. Do I guess any of them have ionospheres? Let's take a temperature of an M star, let's call it like 3,000 Kelvin. Yeah. Come back in 5 minutes, and we'll hear what you have to say about that. Uh-oh. I have that problem too. When someone